Thank you. What about you?
Okay. Ismail, how are you? Okay. So you all can join, huh? Without any problem. Yes.
Faisal couldn't join. Teacher.
Faisal couldn't. But
Yeah.
most of you are in the class. Okay. What was the last topic? You can check the previous classes that I uploaded on YouTube. What was the last topic? You remember? Shahla, what was that? The last topic.
There are only two classes, seismology and skip design.
What was the last one? Okay, let me
Members
So
annotation.
maybe annotation or not.
what?
Member failure criteria, maybe.
Got it. Okay, let me review it again quickly. So, I told you that we have two books in this course. The first one is your textbook, this book that you can yeah, and you can see the content here. And the other one is this one, AISC 360. We call it a specification, and this is for steel structures, AISC, American Institute of Steel Construction. And we mainly work with this one, I mean the specification. But for examples and for problems, for more practice, we check out the book. Okay, I told you that we have different situations, different situation.
Teacher, we can't see anything.
Oh, wait. Okay, this is your book, a steel design that I think I uploaded before. Uh, Steel design, Segway, and the other one is AISC specification. Uh, and as I said, we mainly work on this book, the specification. Uh, the way that it works is depends on the situation, depends on the load situation. We have to check, or we have to pick one of the chapters of this specification or this book. Okay, here you can see it. This is the content. For example, tension members, compression members, beams or flexural members, and these are for this course, fundamental steel design. And uh, as I said, first we need to find our situation. For example, tension or compression or bending, we call it beams. In the other cases, for example, shear. You all know what are these load regimes. Okay, first we start with tension, or the members under tension. When we want to find or when we want to design or check the capacity of a member, we have to find its chapter, and for the tension member, it's chapter D. Chapter D, you can see it. Design of members for tension of AISC 360. Okay, and then inside this chapter, we can find our failure criteria. I explained it once, that when we want to design something, for example, suppose that we want to design a column, okay, for what conditions, for what situations, or for what demands you should be design this column. For example, in one situation you may have crash, okay, or crashing. Sometimes we have, for example, failures in here. When we apply, for example, this type of loading or lateral loading, we may have crashing here. Sometimes we may have different situations, different conditions. If we want to design a member safely, we have to find these failures and make ourselves ready for these type of failures. How? For example, as I explained before, one of the common members under tension in a building is braces. Brace. Okay. I explained brace before, and now I'm going to again explain it. We have some members inside our buildings to prevent lateral loads, such as earthquake. Okay, such as earthquake. For example, I don't know if you uh, heard the news about a new earthquake in Turkey, and if I checked out a couple of failures, and for example, in buildings with uh, weak lateral system, such as braces, they had huge and significant failures. Okay, for example, in a building, if we have steel structure, we have to use these braces, or if we have a concrete building, we have to use shear walls. Okay, but in old buildings, we don't have such thing in this way. Anyway, so one of the members that design in our buildings are braces, and uh, they are actually under compression or tension. So what's going to happen under tension? I showed you once that there are two main types of failure. Suppose that this is a member and we are applying tension. This member is subjected to tension. We show tension with T. The first failure, if you remember this curve, the first failure is here, yielding. And the last failure, or the second one, is here, rupture. Okay, rupture is here. If I want to be specific about it, the rupture is here, but we do not consider this part because it's very we can't open account on this part. We consider here as the rupture or ultimate capacity. We show it with Fu and we show this with Fy. Y stands for yielding, U stands for ultimate. So we have two failures, and when we want to design, we have to make sure that these failures are failures are not gonna happen. Okay, so to check each of these failures, we have specific formulations. Look at here in chapter D, tensile strength. If we want to see the capacity for yielding, we have to follow this equation. And if we want to find the capacity for this equation, for rupture, as I said, we have to follow this equation. Check this equation. As I said, we have Fy and Fu. So you know what are they. You already know what are they. And also we have AG and AE, also we have AN. I explained it once, and now I'm going to explain it again. G stands for gross, and E stands for effective. What are they? This is our member. A is cross section. Okay. What is the cross section here? This is the cross section. Okay. A thickness of T, depth of, for example, B, and what is A? T dot B. Okay. In this part, there is no holes, there is no anything, and gross. This is the A gross. That means the whole section. But suppose that we have some holes inside this plate, like this. Okay, T and B. And there is a hole with diameter of D. Again, this is the whole cross section. Okay, we have tension, we are under tension, and if I want to find AG or the whole cross section, this is the whole cross section is this green part. And what is it? T dot B. But if I want to find another cross section, I told you we have AN and AE. What is this? AN is net cross section, and AE is effective. All here.
So what is the A net?
I'm gonna explain. Okay.
Okay.
What is A net? Let me add a cross section here. Add a section here. What will you see after this section? You'll see something like this. Am I right?
Yeah.
A net is the cross section without considering the holes. We call this A net. Why we should remove or why we should substitute this part? Because this part, let me mark it with red. This red part has no contribution in tension. This part has no contribution in tension. okay? Because we have a gap here. When we want to find the capacity, for example, we have some something here. We have some reactions here. But in this case we don't have anything here. We don't have any reaction here. So we are not gonna consider this part. And if we consider this black area, if we should we show it with AN or net area. Okay. But what is the net area? Net area is A gross minus the area of holes. What is the area of holes? We're not going to consider this as a circle. We consider this as a rectangle.
Rectangular.
T and D. So for this case, we have just one bolt here or one hole here. So AN is equal to T, that's B minus T, that's D. Okay, and we show it with T, B minus D. It's obvious. So for example, in this case, what is AG? AG is equal to this one. This is AG. T dot B. What is AN? Who knows?
3 times of area of hole.
B minus 3D dot T. This is AN. Okay. Any questions so far?
No. Can you show formula one more time?
This one. Okay. Now I want to explain the phenomena of AE, effective area. Okay. We have the concept of effective area when we are connecting two plates, two members together. Okay. This is, for example, one member. For example, this is one member connected to the other member, like this. We have this connection. Let me show you here. For example, in here, if I want to show you better, like this. Here, this member, this is a brace with we call it, for example, a tube member. Okay, connected to this plate, and this plate is called gusset plate. Okay, I'll explain it in future, but right now I'm talking about the connection. This member connected to this member was connected to this plate. Okay, when we have a connection, we have another phenomenon. Okay, let me explain it in this way. Suppose that this is, for example, this is one of for example, suppose that this is a highway, okay, and you have lots of cars in this highway. Okay. Finally, this highway connects to a small road. Okay, so this is the end of the highway. Or let me explain it this way. Suppose that this is the highway, and this is, for example, for some reason, all the cars should pass through this way. You can see that here you have a huge way, but in this blue one you have a small way. What's gonna happen? Do you have any idea? You'll have a traffic here. Am I right? Because there are
Yes.
lots of cars here. Okay. So you'll have a concentration of cars in here. Why? Because the size of these roads are not same. Okay. We have such thing in our connection. AE is equal to U dot AN. You already know what is AN. U is a factor to consider this concentration. How? Suppose that you have a connection like this. If you remember, I explained what is this member. We called it L shape. This is an L shape member. Okay. And this member, like this, for example, in here, if you see, we have a U shape, but in this case, we have an L shape. Let me see if I can find something like this. I can't find it right now, but if you search, you can see. For example, in here we have a L-shaped member. We have an L-shaped member connected to, for example, a plate like this. With what? With bolts. Okay, everything is clear. We have a plate here. What is going on in this connection? We have force flow in all over this member. Okay. But when all this flow want to pass through this connection and go to the other plate, what's gonna happen? This is exactly like what I explained to you before. There are lots of these forces, but there are just, for example, 4 bolts. And just this leg, this is usually one leg, just this leg is connected, not this one. So what's gonna happen? We'll have a traffic in where? In here. All the forces want to pass through these bolts. So we'll have a concentration here. Understood?
Yes.
So, how can we model, how can we simulate, or how can we find this concentration? As I said, there is a factor, we call it U. This factor considers this concentration. Okay, so if I want to design the member, we have to consider this concentration. By what? By using U. U dot AN gives you AE. So you can, if you see the book here, you can see that we are not using AN. We use AE or effective. That I explained it before. I explained it now. You can see effective net area. Okay. Another thing that we have to use when we want to design or when we want to check a section is fee. If you remember, I explained it in our previous classes that when we want to design something or when we want to check something, we have a balance. You remember that balance? In one side, we have demand. In the other side, we have capacity. And in all cases, the capacity not should must be greater than demand. I'm gonna explain with an example. For example, you have 1,000 manat in your pocket. Okay, this is your capacity. So this is your capacity. And you want to buy something, for example, with the price of 900. This is the demand. This is the demand of, for example, the seller. In this case, capacity, that is your money, is more than the demand or the price of that, for example, that thing. So you can buy it, yes? Your money is more than the price of, for example, whatever. So in this case, you are good or you are okay. But suppose that you want to buy something with the price of 1,200. And it is obvious that you can't buy it because your money is less than this. So in here, the capacity, that is your money, is less than the demand or the price. And this is what? Not good. This is the exact concept behind the design. So what is your capacity here? Again, I'm going to explain again. The capacity here, for example, this is your column. The area, the type of, for example, the area, the strength, this is a concrete, for example, column. The strength of concrete, the area, or the size. These items define your capacity. It's obvious the capacity of this column is more than the capacity of this column. Why? Because the size of this column is much greater than the size of this one. For example, sometimes you are using, for example, a concrete with a compressive capacity of 20, and this one has a compressive capacity of 15. Which one is stronger? This one. So size and strength define your capacity. And what is your demand? For example, what is your demand? For example, you want to design a building, or you want to design, for example, you want to design. This is, for example, just a house, an ordinary house, and this one is a football stadium. Okay, max in this building, let me make it big. In this building, you maximum, for example, you'll have 10 people. But in this one, you'll have, for example, 10,000 people. So the demand here is much greater than the demand in here. So the loads, the application of the structure defines the demand. If you remember, I told you that we have different demands. For example, dead load, live load, earthquake, rain, wind, snow, different loads. So it depends on these loads, depends on the situation. For example, if you want to design a building inside the Baku, you have to consider earthquake and wind. But if you want to design, for example, a building in other places, you may not need to, for example, consider wind. So it depends on the situation. You have to pick one of these loads. Anyway, this equation here gives you what? Capacity. Okay, this equation in here gives you the capacity. And the loads in this course, the demand in many of cases will be given. So because you already know how to find the demand from structural analysis. But in this course, I'll give you the demand. For example, I'll tell you that the demand is, for example, B, for example, is 500 kilogram per meter square, or L is 200 kilogram per meter square. Okay, so they are given, but you have to find the total load, dead load and live load. I think you are remember this equation, 1.2D plus 1.6L. We have to find the proper combination between these forces to find our ultimate load, PU, ultimate load. And as I said, this is Pn. Capacity should be greater than demand. But we have to, if you remember, I talked about all of these phenomenon in previous class. All LRFD, load reduction factor design. What was the concept? If you remember, I told you that we have some factors like this, 1.2D, 1.6L, whatever, in our demand, to increase the demand, to make sure that our design is safe. And also we have some reduction, such as phi, to again make sure that our structure is safe. You understand that? These phi is here, or the reduction factor is here. You can see it, LRFD. And in this course, we are not going to use this one, ASD, or allowable stress design. This is an old-fashioned concept, and we're not going to use it anymore, at least in steel structure. Maybe you may use it in soil engineering, but in steel structure or even in concrete structures, it's better to use LRFD because it's a newer method. Okay, you understand it? Yes or no?
Yes, teacher.
Yes.
Okay, so for each equation, we have each equation has its own phi or reduction factor. Okay, let's solve an example to make this clear. Again, let me check the book if we can find an example in the book.
Teacher, what is the topic of this chapter?
Tensile member.
Okay.
Okay. As I said, we have tensile strength. The tensile strength is Pn. The tensile strength for yielding is FyAg, and the tensile strength for fracture or rupture is FuA. And in case that we have connections, we have the factor A. We have to consider AE. Okay, and again, the demand Pu should be less than the capacity, the reduced capacity. Sometimes we show this reduced capacity with Rn, Prn. Okay, let's solve an example like here. Okay,
Sir, we can't see anything.
you sure?
Yes.
What about now?
Hello, teacher. Is there any picture?
What?
I can't see anything.
What about now?
Yes, yes, no, I see.
Yes, I saw.
Okay. Okay, I've been talking about this equation, this example. In here, you can see that there is a gusset plate. Gusset, PL means plate, and a plate. Do you know what that? What does it mean? PL 1/2.5.
Size. It is the size of plates.
Yes. Size of plate. Okay. One point before solving this equation. Suppose that you have a plate. Okay, suppose that you have a plate and you want to make a hole inside this plate like this. For example, for connecting bolts. Do you know how to make this hole? Do you have any idea? Do you know what is drill?
Yeah, I know somehow.
Okay, we have something, for example, that by rotation, by rotating, makes hole inside, for example, plates inside wall. I'm sure that you saw it before, and you know what I'm saying. Let me show you.
Yes, sir, no.
Yes, you know, for example, like this, but in a huge, for example, size. We call this drill. And let me show you again. Okay. When you make hole inside a plate, what's gonna happen? You have a huge hole, for example, here, and you have micro cracks here, but you can't see these cracks with your eyes. Okay, but the capacity of this part, the hole is not here. But the capacity of this part is not stable, or is less than the rest of the plate. Understood?
Yes.
So if you want to design this plate, you cannot consider, or you cannot open account on this area. what should you do? You should consider the hole like this. Okay. At first, you may see that this is, for example, your hole with diameter d. But as I said, because we have a couple of cracks here, micro cracks, we should consider the diameter this one, not that one. How much is this? The diameter of this hole, because of cracks, is equal to, for example, this is the d, or let me write the other, which is the red one. But you have to consider, for example, d prime, the green one. How much is the green one? D prime is equal to d plus what? Something, plus e. And the codes or the books suggest 1/8, if I'm not mistaken. Let me see. Here you can see that 1/8 if you work in inches, or 2 millimeter if you work with SI unit. So, for example, I'm saying that this is your plate with diameter of, for example, 8 millimeter. When you want to find AN, if you remember,
I'm sorry. Which one was D prime? Green one?
the green one, yes, the bigger one is D prime.
What was E?
E, I'm telling you, is something, for example, 1/8 inches or 2 millimeter.
Okay.
If you work with BS like this, if I, for example, in this question, look at the question, it says that we have 4 bolts with diameter of 5/8. Okay, so it says that their nominal diameter is 5/8. But if you remember, if I explained you that we have something here, some cracks. I can't show it here. We have some cracks here. We have some cracks here, like this. Some small cracks here. And we can't, and these parts are not reliable. So we have to consider this hole bigger. The bigger one is D prime, and the smaller one is D. In this question, D is 5/8 inches. What is D prime? 5/8 plus 1/8.
1/8.
But if, for example, the example is in SI unit, for example, the diameter is 8 millimeter. What is D prime? 8 plus 2. Understood? When you work with SI like this, you have to add 2 millimeter. When you work with BS, you have to work with, you have to add 1/8 inches.
Teacher, you always add the 2 or 1/8, or it depends of the size of diameter.
It depends on the unit.
Oh, okay.
Here, all the units are in inch, so you have to add 1/8 inches.
I mean, what if it was a 10 diameter?
10 millimeter, you mean?
Yeah.
When you have 10 millimeter, we have 10 plus 2. If we have, for example, 5 inches, the diameter is 5 plus 1/8.
1/8.
Okay.
Yeah, I understood.
Okay, let's solve the example. I want to check. This is the main title of this example. Find tensile strength. Okay, find tensile strength. So let me write down the it's not working right. Okay. Okay, I told you to find the tensile capacity. Okay, at the first step, in the first step, we have to check the chapter D. Why? Because it's a tensile member. Okay, what we do first? Check the criteria. One of them was yielding, and the other one is rupture. Okay, so for the first one, Pn is equal to F by Ag, and phi is 0.9. Okay, so as I said, we have different failures. The first one is yielding, and at the end we have to yielding, and the other one rupture. At the end, we have to make sure that none of these failures will happen. Okay, I'm gonna name this R1 and this one R2. Okay. What is R1? R1 is VPN. What was PN? And what was phi? Phi is 0.9 and Pn is Fyag. Pn is Fy and phi is 0.9. Fyag. Okay, what is Fy and what is Ag? In here, who knows what is Ag? Maher, do you know what is Ag?
Area of gross.
Gross area, what the value?
You mean formula?
No, the value. I told you it's B dot T. Yeah?
Yeah.
And what is B, what is T here?
1.2 inch.
1 over
dot.
2. Not wrong.
Yeah. Yeah,
Dot.
1 over 2. 5.
Yes. When we see this notation PL 1 over 2.5, that means in this plate the thickness is 1 over 2 and the width is 5. But the length is unknown, and we show unknown length with this one, something like this. Okay, so this is 5, and the area, as Maher said, is 2.5. This is Ag. What about Fy? If you remember, I told you that we have to perform tests to obtain this curve. And Fy and Ag, Fy and Fu are given. So we have to check the question to see how much is Fy. In here, it says that the steel type is A36. Okay, A36 is the steel type. Please memorize it. In A36, Fy is 36 and Fu is 58. Understood?
Yes.
Okay. So everything is clear now. 0.9 dot 36 pound per psi. Kilopound psi dot 2.5 inch square. Okay. The next one is phi. The next one is rupture, and it's again VPN. In this case, what is VPN? For the next one is fu.ae and phi is 0.75. So here we have 0.75 dot FUAE. Okay, I'm gonna explain AE in next class, but now I'm just explain for now. You should know that for this case, AE is equal to UAN, and for this case, U is 1. Let me ask Shahla, what is AN in this case? Can you hear me? What is AN? 5 minus
3 2 dots 3 over 4.
2 dot 3 over 4
Mhm.
dot
T. 1 over 2.
1 over 2. So why this is AN? In here we have 2 bolts. You can see it here. If I add a section cut here, you'll see something like this. You can see that, as I said, the diameter is 5 over 8, but because of the cracks, we have to add 1 over 8 to the diameter, so the final diameter would be 3 over 4. And we have 2 diameters, so the first one is here and the other one is here. The total width is 5, and this one is 5 minus 2 bolts, and each bolt has the diameter of 3 over 4 dot the thickness 1 over 2. So for our case, AN is equal to 5 minus 2.3 over 4 1 over 2. And for now, I explain how to find U in next class. But for now, can assume U as 1. So
Teacher, I have any
what? What did you say? And AE is equal to AN is equal to 107 inches square. So in this case, what was FU? I told you it's 58, and AE is 1 over 1 point. The last thing, the final capacity is minimum of R1 and R2. Let me check the answers. For the first case, PRN is 81. For the second case, PRN is 76. And the answer, as I said, is the minimum one, 76.1. So if I ask you what is the capacity of this plate, where is it? Here. What is the capacity of this plate under tension? You should say it's 76.1 kilo or kips, kilopound. Any question?
No. Can you show the answers, teacher?
Here. For the first one, yielding is 81. For the rupture is 76.
Okay, thank you.
Any other question? Ismail, what did you say? I can't hear you well. I'll record. I recorded the class, so if you have any problem, you can check it again. Okay, see you next time.
Teacher, did you upload the PDFs to here?
I uploaded once, but I think it's gone now. I'll upload it again.
Okay, thank you.
See you.
See you.
Teacher, can you add in YouTube this video?
This video, okay.
See you.